All right, 6.4, factoring polynomials. Some of this is going to be similar to quadratics, but a lot of it's going to be new. So factoring is pretty common. You're probably going to use it more often than synthetic division, to be honest. So you want to be really good at this. So it says if a number can be divided by another number with no remainder, we say that it is a factor. So for instance, I know that 4 goes into 24 evenly. 4 goes into 24 6 times, and I get a remainder of 0. So if that happens, I can say, hey, 4 is definitely a factor of 24. Same thing is true with polynomials. So if you do long division or synthetic division, and you get a remainder of 0, then you know that expression has to be a factor. So let's test. Right now we're going to determine whether or not something is a factor. So to test to see if this is a factor, I'm going to put 3, just like we did in the last lesson. It's got to be in the form x minus a if you're going to do it. So it's kind of like the 0 or the opposite. So 3, and then I'm going to do synthetic division for this one. This is 1, 2, negative 3. So we play the game, slide the 1 down. 3 times 1 is 3. Bring it up, add, multiply, add. And it looks like we do have a remainder of 12. So we know that x minus 3 is not a factor of that polynomial. So it's not a factor. We're looking to get a 0 for a remainder. So I try this next one, and I put negative 4 in here. And we have 2, we have 8. Notice there is no x squared term, so we have to put a 0 there. And then 2 is the x term, 8 is the number, the constant. Let's run it. Slide the 2 down. Negative 4 times 2 is negative 8. Add, you get 0. Negative 4 times 0 is 0. Add, you get 0. Negative 4 times 0 is 0. Add, you get 2. Multiply, you get negative 8. And we do get a remainder of 0. So that means that x plus 4, yes, it is a factor. So that's just a nice little way to use synthetic division and the remainder to see if something is a factor. All right. Now, when you have 4 terms like this, another common method is called factor by grouping. So factor by grouping is going to be not too bad. It's pretty common. Think about this. Think about and you don't have to write this in your notes necessarily, but if you just want to follow me, let's say that I want to use the distributive property for just plain old numbers. All right, just as plain old numbers like 5 times 8 take away 3. Well, if I was going to use the distributive property, I would do 5 times 8, subtract, and then I would go 5 times 3. Well, notice that we have this common number here. We have this 5 that is involved in both pieces of the multiplication. All right. So what we actually can do whenever you see that happen, that 5 can just get factored out, and then you're just left with the 8 minus 3, and you're back to where you started with. Now you might kind of be like, well, why is he going through all this? You're going to see in a second that this exact same thing plays out with polynomials. So what I'm going to do is I'm going to group the first 2 terms right here, and then I'm going to kind of group these second 2 terms, and I'm going to pull out a GCF from them. So in the first one, I'm going to pull out an x squared is the biggest I could pull out. And I would have x plus 3. Well, then over here on the right-hand side, I could pull a negative 4 out of there. And I'm going to have an x plus 3, because that would distribute back to be what's above. Well, notice now we have this common x plus 3. Just like up here, we have this common 5 being multiplied by 2 different things. So what we can do is we can pull that out. We can pull out that x plus 3. And then the 2 things that are left, we can put them in a parenthesis, the x squared minus 4. Sometimes right here you're done. Sometimes it's all over. But remember, the thing on the right there is actually a difference of squares. So I can take this a step further, and I can actually break down or factor that second expression, because x squared minus 4, this is a perfect square, and this is a perfect square. So the difference of squares, This is going to be an x plus 2, x minus 2 situation. So I have now broken this up into 3 factors that all make this original polynomial up above. All right, so let's try the same thing over here for number 4. All right, so this next one I got 4 terms. I'm going to break it up just like I did before. I just kind of write it like that. I know it kind of looks like multiplication, so some people may frown on that and be like, you know, hey, Kraft, you should probably put a plus in there, you know, and do that. And that way it doesn't look like multiplication. So I don't usually do that, but you're probably supposed to. But either way, I'm going to factor out a common factor. I yank out an x squared, and I'll get an x minus 2. Now I'm hoping to either get another x squared or another x minus 2, or factor by grouping won't work. But I see I can pull out a 9. And actually, if you can pull out a negative, it's usually helpful to pull out a negative. So I'm going to pull out a negative 9. And that'll give me my minus 2. If I would have pulled out a positive 9, it would have been a plus 2. So then you'd have realized, man, I'm going to have to make an adjustment. And not all problems can be factored this way, but all the ones that I give you, if I say factor by grouping, you're going to be able to do it by grouping. So again, I have this common piece where I have the x minus 2 in both terms. And then I have the x squared minus 9. And again, this one happens to be the difference of squares. So I can keep going. I can factor it completely. And I can do a plus 3 and a minus 3 and break that all the way down. Now, it's not mandatory. You don't know. I mean, it is mandatory if it's able to, but if you would have had like an x squared minus 7, you really couldn't have went any further. So I don't want you to think you're always going to get it. Review difference of squares. I don't think that's necessary because we just did 2 of them. So I'm going to kind of leave that off. All right, factoring the sum and difference of 2 cubes. So, you know, we had some rules for quadratics that we've just done the difference of squares a couple of times. And sometimes you factor sum of 2 squares. For instance, actually we didn't do a sum of 2 squares for quadratics. But we did for the difference of 2 squares. But for cubes, there's one for both of them. And what I really want you to kind of focus on is the pattern. So notice when you have this a plus b cubed, it's always going to break down. Once you identify who your a is and who your b is, they should fit nicely into these slots where it's always going to be a plus b, and then it's always going to be a squared and b squared on the end. And then the middle is going to be that a times b multiplied together. I think the hardest part to kind of remember, and you're going to get a note card, so you're not really forced to memorize this, but this negative sign here is opposite of this plus sign. So I always kind of remember that it's that center term has the opposite as the other one. And there's a little jingle that I don't really know too well, but I know that you can kind of sing a little song and memorize this, and maybe in class I'll show the YouTube video of it, but I don't really use it. And then the same thing for the difference of the 2. You know, if the subtraction of 2 cubes, the front's going to be subtraction, the middle term's going to be the opposite, but really the a squared and the plus b squared kind of stay the same. So I think if you do enough of them, you'll kind of start to get the feel for it. So let's go through here in a couple steps before we get started. Step 1 is always factor out a greatest common factor if possible. Okay? If you can yank a GCF out, it's just going to make your life a lot easier. So do that first. And then secondly, you're going to want to rewrite as cubes. And I'll show you what I mean by that. Basically, what we need to do is we want to have our a and our b explicitly written out. So when I look at number 5, I have x to the third minus 27. I can't factor out a greatest common factor, but I do see a couple cubes here. So I have x to the third power minus, and 27 is a cube, and it might even be helpful over here to list out the cubes at least the common ones. You know, so 1 to the third power is 1. 2 to the third power is 8. 3 to the third power, 3 times 3 times 3, is 27. 4 to the third power, 16, 64. 5 to the third, 5 times 5 is 25, times another 5 is 125. Usually we don't go much bigger than this. I might do 6. 6 times 6 is 36, times another 6 would be 216. But these numbers here should kind of jump out at you if you see them, to know that they're perfect cubes. Kind of like we know our perfect squares up through 100. But the cubes get really big really quick. So I notice 27 is 3 to the third. So I can rewrite that 27 there as 3 to the third power. So now when you're kind of thinking about this, you know, x is my a, and 3 is my b. So I'm going to use this format up above. I'm going to use this little chart. And I know I'm going to follow this pattern because it's subtraction. So I'm just going to put the a's and the b's in the right places. So the first parenthesis should be a minus b. So in this case, it's just going to be the x minus 3. And then something that stays true with both of them, so I kind of always do it this way. I square the first term. I square the last term. 3 squared is 9. And then I got to remember, this is the tricky part, I got to remember that in the middle I multiply them together and it's the opposite. So it's plus 3 times x. And then if I could go a little further, but I can't, you know, I can't factor that last part. So right here is, I've factored those 2 cubes that are subtracted from each other. All right, let's give the next one a shot. Well, on the next one, I can do step 1 here. I can pull an 8 out. So I'm going to yank an 8 out of there first. And I'm going to get x to the third minus 8. And it's looking like it's going to be a difference one again. So it's going to be this same type of idea. And 8, I notice, can be written as 2 to the third. So I'm going to have 8 times x to the third minus 2 to the third. So it's kind of like in this scenario, a is x and my b is going to be 2. So I'm going to kind of play the same game I played before. I'm going to do a minus b, which is x minus 2. Then I square the first, and I square the last, and then it's the opposite multiplied together. Whoop, I almost put a 4 there on accident. I was looking at that back 4. My a and b were 2 and x, so I have to multiply 2 times x. And there would be our final answer. I'm going to slide down a little bit just so I can have a little more room on these next two. So slide it on down. Better keep my, now let's see if I can remember it without my chart. Just test ourselves here. Test myself. You have your paper in front of you, I guess. So I'm going to pull out the greatest common factor, which I can yank out of 5. And I can yank out, whoop, got a little excited there. Can yank out a 5 and an x. Pull everything out you can. And that's going to give me an x to the third plus 8. Which again, this one's going to be the sum. So this is going to be that top example in the chart. So I have the sum of 2 cubes. So I already did step 1. Step 2, let's write them. So I'm going to go 5x times x to the third plus 2 to the third. So that's where I'm writing them as cubes. And now I have my a and b. You know, so if you want to kind of really small under here, there's my a, there's my b. And let's kind of run this thing. So I got 5x. I then do my a plus b. So x plus 2. Then I'm going to square the first one. I'm going to square the second one. And then it's the opposite. So since I was adding up there 2 cubes, it's the opposite of those 2 multiplied together. Don't lose your 5x though. All right? That's still going to be part of it. And I wonder if up above I think up above I might have forgot to keep my 8 in there. I don't remember, but if I scroll up now it's gone. But hopefully in that last problem, that 8 that I pulled out, hopefully I had that in my final answer. If I didn't, go back and add it in there. All right, this number 8 is a little bit trickier because I can't pull a number out of 8 and 125. There are no common factors there. So I got to be kind of slick about how I write this. Well, I do notice that this number and this number are both perfect cubes. So I could rewrite this one as 2y to the third, because 2 to the third is 8, y to the third is y to the third. So I wrote, so really that's my a. My a is 2y. And then subtract, it looks like 5 to the third is 125. So I've written this as my two, as my two cubes. So here's my a, there is my b. And now I'm going to run this through. This is the difference. So we start off by, it's just a minus b. Square the first term. Square the last term. And then it's the opposite times the middle together. So the opposite is going to be plus. And I got times 5 times 2y, which would be 10y. No greatest common factor to worry about. So I believe I'm good to go here. So you just need a little bit of reps, some drill and kill to kind of make that settle in and sink for you. All right, graphs here. It says you can also use a graph to help factor a function. Remember that if you know the zeros of a function, so wherever it crosses the x-axis, if you know those zeros, you can work backwards to get the factors. Don't write this in your notes, but if you remember in chapter 5, when we were, sorry about that. In chapter 5, when we were doing quadratics, if I gave you the zeros, you could work backwards to get the factors and then eventually get the original function. So, if I have this, I think I kind of did it like this. Like, let's say that you know the zeros are, x equals 2 and x equals negative 5. All right? So maybe on a graph, you somehow knew that you had a 0 there at 2 and you had a 0 there at negative 5. Well, it kind of told me about the parabola, depending on if it is concave up or down. We kind of knew that it looked something like this. And we could actually find the function because what we did was, if these are the zeros, I don't know why I put an E on there. If those were the zeros, we could work backwards and get the factors. And then we could multiply it out and actually find the original function that made that graph. So we had that on one of our tests. So we're going to do something similar here. Looking at this graph, I see 1, 0. I see a 0 right there. And it looks like this grid's going by 3s. So I have a 0 at x equals positive 24. So that tells me right there that I have a factor. I have something that goes in there evenly of x minus 24. Now, I don't know right away, x minus 24, it goes into it evenly, but I don't know by how many times. So I could either use long division, or I'm going to cheat and use synthetic division. It's not really cheating. But I'm going to put my 24 here, and I'm going to use all of these coefficients. Negative 1, 32, negative 224, 768. I don't really have to worry about putting 0 in because all the x's are accounted for. But because x minus 24 is a factor, I know that this thing should have a remainder of 0, and I should get the answer here. So let's slide the negative 1 down, multiply, add, multiply. I wrote this down. This was 192. And then I add, and I multiply. And I'm like, yep, it definitely comes out to be 0. But I knew it was going to, because I already knew x minus 24 was a factor. But what it gives me is it gives me the other piece. So since this is x to the third, got to go 1 less. This is x squared This is x, and this is my number. So I now have the other factor. So one factor is x minus 24. Got that from the graph. Synthetic division gives me this other factor right here. And now I have both factors that give me that expression up above. But without the graph, I really couldn't have got started. Maybe I could have done some sort of grouping. The numbers are kind of big and nasty. But if you have a graph, you can actually cheat and use it. Now, some people would probably frown on me leaving that negative in front of the x squared. So they might be like, hey, Kraft, you really should pull a negative 1 out of this, over here, and call that x squared minus 8x plus 32. You really should yank that negative 1 out of there. Kind of do something like that. And typically when we do it, looks kind of goofy, but when we do it, when I yank a negative 1 out, I usually just pull it all the way out to the front and just put a negative there. So, but the big thing I want you to understand is the graphing part. So this next one's actually pretty nice because they give me 3 zeros. So I'm like, sweet. If my zeros are at x equals 1, x equals 3, x equals 4, my factors are going to be x minus 1, x minus 3, x minus 4. And I don't even have to do synthetic division because that accounted for all of them. That's the whole thing. That's everything. So you'll notice this other one, it didn't come down low enough to give me a couple more zeros. So that's why I didn't get all 3 of them with once. Where this one, it went above the axis, below the axis, back above, and it hooked me up with my answer without really doing any work. All right, hopefully that's enough to get you ready for the practice. If you have any more questions, we can talk about it in class. See you.